Cool. So hopefully everybody can hear me. Oh, this is way ahead of where it should be. Hold on. Pretend you're not seeing any of this. You have no idea what's going on. All right. Hello. Thank you. I'm Paul Dix. I'm working on InfluxDB, which is an open source time series database that me and some people are building. So I think what's useful to start is what it's for. Why would we make such a thing? Well, it's useful for metrics data. So this is like data that's coming off of your servers or in your applications. It's very common in the DevOps use case. It's useful for time series data. A lot of people in New York love these things. But it's also useful for real-time user analytics and business intelligence. And the other thing it's good for is events. So this is an Apache log that I downloaded, I found. And when I see this, what I actually see is a bunch of different time series, right? You can have how many 200s there were per minute for the last 5 hours. You can have how many errors there were. You can have how many 200s there were to a specific URL. So you can induce hundreds or thousands of time series just from this event stream, right? So the use cases. I mentioned DevOps. That's a big one, right? Tracking what's going on in your servers, in your applications. Another one is real-time analytics, user analytics, business intelligence, that kind of stuff. And then the last one that we're really targeting is sensor data. So this is IoT, both consumer and industrial, right? You're thinking power generation, oil and gas wells, and then on the consumer side, you know, fitness trackers to smart home stuff, all that kind of stuff. And those, the sensor data and the DevOps data spaces, they look surprisingly similar. Because when you think about DevOps data and you think about the metrics that you're collecting, the sensors are just software that you have on your servers. Whereas in sensor data, it's the actual physical devices that are transmitting, you know, readings that you're taking. So this is the question that most people ask me when I tell them I'm working on a time series database, right? It's just like a regular database guy, order by time. Been able to do this for a long time, right? So there are a few reasons why we would actually create a database that's specific for time series. The first one is that it doesn't scale in a regular database, right? So here's an example from the metrics use case. Say we're taking 100 measurements per host, which is actually on the low side, and we have 10 hosts. And we're collecting these measurements every 10 seconds. So over the course of a year, that's going to be 3 billion records, right? I don't want to deal with a SQL table that has that many records in it, and nobody else does. So then you're like, okay, well, let's keep summaries. We don't have to keep, you know, every 10 seconds for an entire year. So what we'll do is we'll just compute 1 hour averages. And you're still generating 8 million records a year. And then when you do that, you lose detail, and you lose the ability to do ad hoc queries against high precision data and get some sort of answer on the fly. So then the other thing you think is, okay, well, let's use HBase or Cassandra or some distributed database where we can actually just use an entire cluster of machines. That'll scale, right? And the problem there is it's too much application code and it's too much complexity. So I've actually built a quote-unquote time series database on top of Cassandra on 2 separate occasions. One for a fintech company and another for a metrics SaaS developer monitoring thing. And the thing is, like, the code that you have to write and the things that you have to do to make these distributed databases actually work is a lot more complicated than you think. You have to write application level logic and scripts to compute the summaries for you because they won't do it automatically. This is the trickiest bit, right? Cassandra is a distributed database, so you figure you don't have to think about how to make it distributed. But in the time series use case, when you're writing data in Cassandra, the common way to do it for time series is you have what's called a wide row. And a row in Cassandra and these other databases basically goes down to a single replication group in your cluster. So you could have a cluster of 100 machines, and this wide row is only going to be hot for reads and writes on 3 of those machines if your replication factor is 3. So then you have to write application level code to figure out, okay, for this time series data, we're going to divide it up into these different rows, and then we're going to have to figure out how to compose that together on the fly when people execute a query. And then the other thing is you don't get data locality, right? So for this time series database on top of Cassandra, what you're doing is you're writing web services that are hitting Cassandra and pulling back data, right? So the problem is if you want to downsample and aggregate from raw data, what it does is it hits Cassandra, pulls all the data over the network, computes the summary ticks, and sends it out to the user, right? This is the key thing that we learned from Hadoop and Google's MapReduce framework, which is you want to ship the code to where the data lives, not the other way around. So we wanted something that could do that. And then the last one is this. How do you handle data retention? So with time series data, it's very common to have high precision data that you keep around for a limited window of time. Call it 7 days or 30 days. You aggregate and downsample from that into medium precision and then low precision that you keep around for longer term trends. Now, the problem this creates is that when you're up at your time envelope for that entire period, in theory, if you were actually going to rotate the retention of the data, you're doing just as many deletes as you're doing writes. And databases really aren't designed for this use case. In Cassandra, for instance, a delete is actually more expensive than a write because what it does is it does a write and then later on it does a compaction. So what you end up having to do to make a regular database work with this weirdo user load, which is as many deletes as you have writes, is you have to shard the data out into either different tables or different column families and then drop those. So then there's more on top of that. And that's, if you're, most of this time, if it's time series data, you want to expose an API. And you want to expose the API for monitoring or for graphing things, right? So you have to write web services. And then you have to write libraries for the web services, front-end JavaScript and whatever back-end language you're using. And then you have to write libraries for data collection, pulling data out of your apps, pulling data off your servers or off your sensors, and write tools for visualization. So this is, I'm quoting myself in my own talk. Building an application with an analytics component today is like building a web application in 1998. You spend months and millions of dollars building infrastructure before you get to the actual thing you want to build that's driving user value, right? Analytics and monitoring should be about analyzing and interpreting the data, not the infrastructure that you use and set up to store and process it. And that's why we're creating Influx. It's an open source time series database with no external dependencies. So what that means is it's a single binary, you drop it on a server, and you're good to go. You don't have to install Zookeeper or Cassandra or some other thing to actually get it to work. We want it to be really easy to set up. So I'll talk really quickly about the features. And these features are focused on our upcoming release. We have release candidates out right now, mainly for API testing. This release will be out within the next 3 to 8 weeks, I think. So the basic data model, you have databases, like in a SQL database. You have this concept of measurements that you're taking. It's just a string that identifies a measurement. It could be CPU load, temperature, log lines, a click, memory utilization, whatever the thing is that you're measuring. Then you have tags that are tied to the measurements themselves. These are the things, these are metadata that describe the thing, right? It could be the region that you're pulling the data from. It could be the host that it's coming from. If it's a sensor, it could be like the building that you're pulling it from, or it could be the service, or the application. So with InfluxDB, a series is basically represented by the combination of the measurement and the unique tag set. And within that series, you have a bunch of data points. They have timestamps, which are nanosecond epochs, and then they have non-indexed data called fields. And those can be a bool, an int64, a float64, a string, or just raw bytes. So writing the data is super simple. We have an HTTP API. You just do a post to /write. You put in some JSON that looks kind of like this. You specify the database you're writing into. You specify a retention policy. So you can set up retention policies for different intervals of time. And then you specify the actual data points themselves. Within the data points, you see that we have a measurement name. We have tags that describe the data point. We have a timestamp. And then we have the fields. When you write data, so the entire thing is basically schema on the fly. It creates the schema as you're writing the data. So once you write this in, we remember all this stuff. So querying data is really easy. The entire HTTP API is these two endpoints, write and a get to /query. So for this, we actually created our own kind of query language, and we took SQL and bastardized it for our own purposes. So here we're getting value, which is a field from the measurement CPU, where the host tag is equal to server A. And there we see the results that come back. And the values are time ordered, where you have a timestamp, and then the value itself. So here's one where we're getting multiple series in one query, where host equals server A or host equals server B. We see that we have two result sets in series, one with the tags host server A and the other with the tag host server B. Here's an example where we're computing an aggregate on the fly from raw data. So we're getting the 90th percentile of value from CPU for the last 4 hours in 10-minute buckets. And the group by region means we're going to get a separate series for each unique region that we have. So this is going to give us an aggregation of whatever the 90th percentile CPU utilization is for each region that we're looking at, that we're collecting data from. You can also do multiple aggregates in a single query. So we have mean, percentile, min, max. There are a bunch of different aggregate functions, standard deviation. We'll be adding more. Or you can do something like this, which, depending on how many series you have, could be a very bad idea. Basically, this is the mean value for the last 48 hours in 1 hour buckets. The group by star on the query means to expand it out into as many unique series as we have within CPU. So the InfluxDB is actually, it's kind of like two databases in one. So there's the time series database, and that's useful for storing both regular and irregular time series. Regular is collected on fixed intervals, like once every 10 seconds. Irregular is like event-driven time series. But then the other piece is an inverted index that we keep in memory that lets you do discovery based on the tags that you're writing in. So here are some quick examples there. Here we're just saying show measurements. What measurements are we taking in this database? And it will just give you a collection of those. Here's show series. So basically we would get per measurement, we'd get a series object, and we'd see the columns are actually the ID, and then the other columns are the tags. So we can see what all the unique tag combinations there are that we're collecting. Here we can filter it. So show what measurements we're taking for Redis, for example. With this query, we can just see instantly, like, OK, we're taking all these measurements within Redis. Or we can say, OK, what are the keys for a given measurement, right? So for CPU, what keys are we writing in to describe the data? So here we see region and host. Or we can filter it down even more and say, OK, what different values do we have for the key service? So this will show us what services we're actually collecting data for. And finally, you can pair that up with the measurement name itself. So what tag values do we have in the CPU measurement with the key service? That's just a taste of some of the stuff that you can do as far as like querying and discovery and that kind of stuff. It's basically the time series stuff and then kind of a discovery engine to see like what you're collecting. So the other things that I touched on very briefly, retention policies. This is handled for you automatically by the database. Automatic downsampling and aggregation. It's a feature we call continuous queries. Basically, for any of the queries that you can issue, you can tell the database, run this query in the background continuously so that you can then visualize, like put dashboards around like downsampled, lower precision data. And then finally, there's clustering. The last bit I wanted to show off was actually not a project that we did, but a developer in Stockholm wrote this. It's an open source tool for creating dashboards and visualizations around data that's either in InfluxDB or Graphite or OpenTSDB. And we find that most of the people using InfluxDB use this to visualize their data and create dashboards for all the data that's going into Influx. And that's all I have. Thanks.
With 3 seconds to go, how perfect is this on timing?
Nice.
Very well done. tell us maybe just a little bit about yourself, the history of the company, the joys of building a data company in New York, all those things.
Yeah.
And then we'll take a couple of questions.
Okay. So myself, I'm an engineer. I have a CS degree from Columbia, so been in New York like 10 years. I also am the series editor for a book and video series for Addison Wesley called Data and Analytics. So if you want to write a book or you want to do a video on something in the data or analytics space, hit me up. We're always looking for more people. So we started the company originally in late 2012, my co-founder Todd and I. And at the time, we were building a SaaS application for doing real-time metrics and monitoring of the metrics. It was basically in the server monitoring space. We got into YC for Winter 13, did that and worked on that product until about September of 2013. And over the course of doing that, we found that people were more interested in the infrastructure that we were building than the actual application that we were building on top of it. So we looked at the open source time series space and found that nobody was really focused on it, and it seemed like a need that was emerging. So basically in September of 2013, we decided to build version 4 of that SaaS API, but build it as an open source project, which was InfluxDB. So took off in popularity. We raised a Series A that closed last November from Mayfield and Trinity. So, yeah.
Very cool. Congratulations. All right. Want to open to questions? Like 0 and then 20 ends. Whoever is. Do we have a mic in the back or? Yes. You get to choose.
I think I won because I'm closest. So you talked about the fact that if you don't use a database like this, you end up storing a massive amount of data, like a row for every single record. How does this address this? Like aside from the retention policy, which sounds like it automatically aggregates like once the time has passed, do you have any idea of how much space you actually save when you have like 10-second requests?
Well, so it's really not about compression. It's more about how you shard the data across multiple servers and how you read it. Basically, if you're for a SQL database, for instance, like the most basic way to create time series data in SQL is like to have a measurement name and a timestamp and index by both of those. And the thing is, as you insert more data into the table, it's just going to get big and a pain to use. Under the hood, we just use a key value store where the key space is ordered, and it's cheap to insert. So as far as the amount of space, when you send in a measurement name and a tag set, we compress all of that down into a single ID, a single 8-byte ID. So what we store is for our data store, we basically create a separate area in the database for each series ID. So what we end up storing is a key, which is an 8-byte timestamp, and then whatever the values are. So it's fairly compressed, but we're not actually using any compression under the hood, like Snappy or anything like that.
Quick other question.
Hi, I'm curious, when you talked about some financial technology applications you guys had done, I think a bit earlier. When you work in that world, where you often have periodic time series, do you have any functionality built in to kind of optimize the analysis of that kind of data when it's a periodic time series?
You mean like your regular time series, like trades and stuff like that?
Either trades or things that give you updates on values of something, every second or every minute that allow you to kind of go back and do the calculations very quickly.
Yeah, I mean the key thing is being able to do the calculations on the fly, to compute aggregates on the fly. So under the covers, we basically have our own MapReduce implementation that's tightly focused on this use case. So for some of the queries, it's able to do that, distribute it very effectively. Like min and max are very, very easy to distribute. One that isn't is like percentiles, for instance, right? To do percentiles, you'd actually have to transmit all the raw data. So we will have things later on to do approximate percentiles, but I know there are some people in finance that have used it to create like a risk dashboard.
I was going to say like things like moving averages and correlations and
Yeah,
all that
moving
stuff.
averages on our to-do list.
Okay.
But yeah, like I know there are people who've created like a risk dashboard on top of it, where they have like a dashboard and they can just look at it to see what's going on, and they mix in data from their algos and their trades with market data that's being pulled in. So it's not, the use case isn't for critical path for like a trading algo. For that, it would be, you'd want something totally custom that has guaranteed response time sub millisecond. Right. This is written in Go, so which is a garbage collected language. So worst case response time can be worse than what you would want in that kind of setup.
Okay, thanks.
Great. Time for one last question, maybe in the back or on the. Sorry to make you run.
Hi. So time series analysis has been is a function that's been performed by several databases that have been around for a while, including open source databases like KDB. Just want to understand what is the how do you differ from a product like KDB philosophically or in terms of feature functionality or where you're going?
Yeah. Is KDB open source?
I
didn't think it was open source.
I'm sorry. There's a free version, not open source. I'm sorry.
Right.
There's a
Right.
32-bit free version and a.
Right.
Yeah.
Yeah, so I'm not quite sure how to answer that because I'm not as familiar with KDB as I could be. They seem to be mainly targeted on finance, whereas finance is not what we're targeting at all right now. If people in finance happen to use Influx, that's great. We'd love more users, and it's certainly useful for some of that. But KDB is written in C++. It has different guarantees about performance. They've been around for a lot longer, so on some fronts they're definitely farther along than we are. But what we try to do is, I think the continuous query stuff, the automatic aggregation and downsampling is kind of unique compared to KDB. I don't think they're really doing that. And I'm not sure what kinds of data you can store in KDB versus other kinds.
Good. Thank you.
Great. Well, that's all the time we have. You're going to be around after this?
Yeah, I'll stick around.
Wonderful. Thank you very much for being here.
Thanks.